Okay, last class we have focused on photodiodes. Now let us start discussing on PN junction as a solar cell. It's a topic. Okay, solar cell, you know that it is a basic diode PN junction, wherein which you can extract the harness the solar energy and convert that into electrical energy. If you want to write a block diagram for this solar cell, okay, so input is going to be the sunlight or photons, okay, and output is going to be the a current, electrical current, which is nothing but current I. So this is input and this is the output, and here we have solar cell. Okay, so solar cell basically it's a PN junction that converts incoming photons into the equivalent electrical energy. We'll see that how. This symbolic representation of solar cell is almost the same as photodiode. There is no much difference in the photodiode. It's the diode symbol only. But we have here two line that shows that there is an photons which are injected onto the diode surface. The reference voltage across this solar cell, let us take it as VD, which is the diode voltage VD, and current flowing through this due to the incident photons, let us take it as ID. Okay, so this is the current flowing through the diode. Physical structure, if you observe solar cell, the internal structure of this, which resembles this, as you are seeing here, it has got different, the materials you can see here. This is a N-type semiconductor region, N layer, what you can see here. This shaded region, this represents N-type semiconductor, and bottom we have P-type semiconductor region. So this region which is below this, we have a P-type semiconductor region, and there is a back contact also, you can see, which is a shaded portion here. This represents back contact. On top of this you can see there is an anti-reflection coating here. It is empty spaces which has got anti-reflection coating. This avoids the reflection of this photons to other region. It tries to focus this the photons onto the semiconductor surface. Okay, that's the basic necessity of this anti-reflection coating. So here we need to apply the photons is considered as H into mu. This is the photon energy that's falling on the solar cell surface. Okay, so this dark shaded portions what you see here, this is shaded portion. These are nothing but they are the metal contacts. This looks like in a finger fashion. If you look at the 3D view, which is shown here, so this is a three-dimensional view of a solar cell. It looks like a finger. Okay, so this is a 3D structure of the solar cell. So here you can see is a cross-sectional view. Therefore, you see this metal contacts looks like a finger. This is a single metal what you are seeing as you are observing here. Okay, so this is the physical structure of the solar cell. And next, let us look at a three-dimensional view. Three-dimensional view is almost same. You can see here there is a N region here. This is N region. This is a P region, and there is a junction between N and P region here. And these are all contacts which looks like a finger, and bottom contact is not visible to you, or back contact is not visible to you here in this 3D view. Okay, and here we need to make the light to fall on this. That converts into the, if you make this as a closed circuit, you will get a current equivalent of the light which is impact on this surface of this the solar cell. Okay. Next, coming to the characteristics of this solar cell, we have shown here this complete photodiode characteristics, but here the application, real application of this solar cell lies in the fourth quadrant. Okay, we have already seen this in the last class. Why we operate use photodiode in the fourth quadrant? If you want to extract energy from this solar cell, you need to operate this solar cell in the fourth quadrant. How do you operate this in the fourth quadrant? That means the applied voltage is positive, the current whatever you get it is negative here. Okay, So, in this region if you operate here, this is the region of operation of a solar cell. Okay. So, maybe at some point of operation. Okay. So, this is called operating point. At some operating point you can extract maximum energy from the solar cell here. So, we will describe that the which point you need to choose, how to choose this point to harness a maximum amount of the solar energy from the solar cell. Okay. This is the quadrant region of operation of solar cell. Now, let us look into the energy band diagram of solar cell. If you look at energy band diagram, this looks like almost like a PN junction energy band diagram. There is a P region here, there is an N region here, there is strong electric field acting from N to P. Okay. So, you can see here this now if you light rays or light H into mu, if you apply this photon energy which is far greater than the band gap energy here. So, electron hole pairs are created because of this H into mu is greater than Eg. This creates electron hole pair. This is called the carrier generation. This is the carrier generation. You can see electron is here and corresponding hole is here, and the field here is very strong that it pushes the electrons to the N region and hold to the P region here. Okay. So, this is what you are seeing, the arrow marks here, electron moving. This shows arrow mark shows that electron moving into the N region. So, here the drift process comes into the picture. So, electrons are drifted to the N region and holes are drifted towards P region here. This is what it is mentioned here. There is a strong electric field which is acting from N to P side, and the current flows due to the photons flows from N side to the P side here. So, this is the direction of current here. IL, okay, current due to the light or illumination is taken as IL, that flows from N side to the P side. So, this is an energy band diagram here. Though electron hole pair happens in the neutral N region here, this region and this region here. So, this is almost negligible because this is a neutral P region and this is neutral N region here, and here the diffusion process will happen, and even here also since diffusion process is very slow, even though if electron hole pairs are created here. Okay. So, the diffusion process will make the electron to diffuse to the edge of depletion region here. Okay. If this thing happens here, if diffusion process makes this electron to move towards edge of this depletion region, then here the drift process will takes this electron which is coming here and it pushes this electron to the N side, and this hole, if it comes due to the diffusion process here, again the drift process will push this hole back to the P region itself, because the hole moment and the field are same here. Okay. So, field is acting from N side to P side. So, in the corresponding direction hole will be pushed back into the P region. Okay. So, this is what happens in the neutral P region and neutral N region. Okay. Now, let us see the equivalent circuit of the solar cell. Solar cell equivalent circuit, we have already seen the symbolic representation of a solar cell. This is the symbolic representation of a solar cell. In ordinary PN junction diode with two lines, this shows that it is a solar cell. The current that flowing through this solar cell is ID, and VD is the voltage across this solar cell. An equivalent circuit can be designed for this solar cell. So, here we write the ordinary PN junction diode, okay, with a diode symbol here, and parallel to this we show with a current source here. This current source is because of the photons when they are injected onto the diode surface, it leads to the current flow within this the solar cell. So, this current flow from N side to P side, this is N side and this is P side. Because of the photons, current flows from N to P. So, this current is shown as, the flow here is shown as a current source here, IL, with the magnitude of current as IL, and it flows from N side to the P side here. This is the current source here. If you do not allow this light here, if there is no photons injected onto the diode surface, and this current will not be there, this will act like an open circuit, and complete photodiode solar cell behaves like a ordinary diode. Okay. And we know that ordinary diode, the current flowing through that is given by this math equation, ID is equal to I naught into e to the power of Vd by Vt minus 1. If light is made to fall on this solar cell, okay, so on this solar cell, then this corresponding current will result, and this current is in a reverse direction compared to the forward current what it is flowing here. Now, total current now this ID minus IL, current due to the forward direction, this is ID which flows from P side to the N side, and this current is flows from N side to the P side. So, these two currents are going to be opposite in direction here. Okay. So, in the absence of light this current source will not be there, in the presence of light this current source will be there, and forward direction in the absence of light this only ID will flow, in the presence of light both IL and ID will flow, and of course, these two are going to be in opposite direction here. Okay. So, this is the equivalent circuit of the solar cell. Okay. And now, this can be written in the mathematical form here. You can see here this is the total current flowing through the solar cell ID, this is the total current is nothing but I naught into to the power of Vd by Vt minus 1 minus IL. This current is due to the illumination of light across the solar cell. Okay. Now, let us calculate the extreme conditions with open circuit voltage and the short circuit current. The reason for doing this is I am trying to estimate the limits of this. Okay. So, as we said already, this solar cell to extract energy to use this as a energy source, we must operate in the fourth quadrant. So, in the fourth quadrant to find out extreme limits. So, you can say this to find out this VOC, I need to short circuit here. So, we open circuit here. So, open circuit in the sense, so the current will not flow here. So, therefore, I will be equal to 0 here. When you open circuit there will be no current here, and to find out this extreme limit ISC you must short circuit the voltage source across this photodiode. Okay. So, short circuit in the sense you must just short circuit like this. Open circuit means you not connect any connection between this anode and cathode should be kept open. Okay. So, in that way you can find out VOC and ISC here. Now, let us see the mathematical equations to obtain VOC. VOC open circuit voltage is equivalent to the voltage across diode under the condition ID is equal to 0. Okay. So, when you make open circuit across the photodiode, so when we kept photodiode under open conditions, this is the photodiode or solar cell, when it is kept under the open condition, current will not flow through this. So, there is a voltage across this. Okay. So, we can write this as VOC, this is equal to VD under the condition. So, open circuit, so therefore, ID will be equal to 0. Now, we can substitute this in this equation 1. So, what happens to equation 1? So, when ID is equal to 0, you can see that the left hand side becomes 0 and right hand side we have left out with I naught into e to the power of Vd by Vt. So, Vt is nothing but it is Kt by Q. Okay. So, this is the Vt is nothing but thermal voltage, this value is nothing but 25 millivolt. If you substitute all this at room temperature, and if Boltzmann constant and charge is substituted, you will get this value. Okay. So, minus 1 minus IL, this is the current is kept as it is. Now, you can rearrange this each and every terms here, and you can substitute in place of Vd as VOC. Okay. And so, if you do that, the resulting equation will be as shown here. So, VOC if you take a natural logarithm on both sides, VOC will be equal to Vt ln of IL by I naught plus 1. This is the open circuit voltage. Okay. Next is to calculate short circuit current, you must make voltage as 0. So, short circuit current ISC will be equal to ID, okay, under the condition Vd is equal to 0. So, when you maintain a short circuit across this photodiode, okay, so short circuit across this, the current flowing through this, okay, it flows from N to P. So, current is in this direction. So, this current is nothing but ISC. Okay. So, this is anode and this is cathode. Okay. In terms of semiconductor, this is a P type and this is going to be the N. Always in the photodiode you must operate in reverse bias, therefore, current flows from N to P. So, therefore, when you make ISC equals ID, so V by considering condition as Vd is equal to 0. So, in this equation 1, so since the numerator you can see here in this equation, when you make Vd as 0, this complete term will become 0. So, the e to the power of 0 is nothing but 1, this is what we have done. This 1 minus 1 cancels here and this complete term will get eliminated, and you are left out with ID is equal to minus IL. So, So, this can be equated to short circuit current ISC, because across the solar cell we have maintained short circuit here. So, ID is equal to minus IL is equal to ISC. Minus is because current is flowing from N to P. Okay, P to N is taken as positive and N to P is taken as negative. So, therefore, the short circuit current is minus IL. Okay. Now, we came to know that the extreme conditions, these extreme limits, one is ISC, which we got to this value as equal to minus IL, and this VOC we got equation as VT times the ln. Okay, this is the equation VT ln of IL by I naught plus 1. So, using these two, you can now find out the extreme limits here. So, for the simplicity here, we can shift this curve into the first quadrant here by making the negative IL as a positive IL. So, you will get correct characteristics of this nature. You can see that here. So, IS now, which is equal to the modulus, let me indicate here IL. So, then you can see the quadrant in the curves in the first quadrant here. Okay, for the simplicity we do this, and here we can do some analysis on this. So, these are the extreme points just now we have identified here. If we extend this the line, and if you find intersection point here, so this is nothing but it is a product of ISC and VOC. You can see the region here, this is a bigger the square area which you can find here. The product of VOC into ISC, that is nothing but which is maximum energy which you can extract from the solar. This ideal energy which you can extract from the solar cell is VOC times ISC. But now practically if you observe it here, so this is the maximum energy, of course, VOC into ISC. If you can choose the point on this curve, so that area under this curve should be maximum here. In case if I choose this point here, the current is I1 and the voltage, let us say V1 here, the area covered under this region is minimum. And even if I choose here this point here, one of the point, if I choose this as a point here, let us call this as P2 and this as P1. Okay, so this as P2. Okay, you can observe here corresponding to this current, let me take it as I2 and this voltage as V2. Even the area region under this curve also it is going to be small. Now, it all depends on now which point you should choose. The operating point must be chosen such that the region under this curve should be maximum. So, now see this P2 or P1, the area under this curve is going to be small. So, therefore, you cannot extract maximum energy by choosing these 2 points. Let us assume that this is a point which is a mid, okay, which is say this gives you Vm, and corresponding to this current let us say Im. Okay. Now, this Pm will be equal to P max or Pm. Okay, this can be equated to Pm. If I call that as product of Vm into Im, and the area under this you can see that it is maximum compared to the regions what you see with reference to P1 and P2 here. So, therefore, if you choose the Pm as an operating point here, you can extract maximum energy from the solar cell. Okay. So, this is Pm is nothing but a point here on the curve where you have maximum area under this curve here. So, this gives us extraction of maximum energy from the solar cell. And there is a definition term here called as a fill factor, which is nothing but ratio of Pm to the P max. Okay. So, Pm to the Pm in the sense it is Vm times Im, and P max here, let me remove this, let us call this as P max. Okay. So, now you can see that here Pm to the ratio of P max. So, this is called as okay. So, P max is called as fill factor. Okay. Pm we already know that it is a product of, it is a region which is subset of this VOC and ISC. So, therefore, this region will be a smaller compared to the big the square area here. So, therefore, this fill factor should be less than 1 always. So, whenever you choose this the region equal to 1, then definitely, so you are extracting large energy from the solar cell here. Okay. So, this is the curve what you are seeing after flipping into the first quadrant from the fourth quadrant here, which is redrawn here. So, this is one of the definition which is a fill factor. Fill factor is now Vm Im divided by VOC into ISC. Now, let us look at other definitions like conversion efficiency. Conversion efficiency of the solar cell can be labeled as eta, which is given by Vm times Im divided by incident power. This incident power due to the photons. Okay. So, now you can see that you can simplify this equation by substituting for Vm Im. From the above relation, you can see fill factor, this Vm Im. So, this can be written as Vm times Im. So, this can be written as fill factor times VOC into ISC. Okay. So, this relation can be substituted here, fill factor times VOC into ISC, then you get conversion efficiency formula. So, which is P in is nothing but it is the incident power which is due to the photons. So, this is very important, these two relations. Kindly remember these formulas, these formulas can be used to solve worked examples and exercises problems given in the textbook here. Okay. I think with that we have completed almost a solar cell. We have seen the symbolic representation of solar cell, characteristics of a solar cell, structure, physical structure of a solar cell, energy band diagram, equivalent circuit, and extreme limits of the solar cell operation. Then we have seen flipping the actual characteristics to the first quadrant and identifying the region of maximum area under this characteristics, and then we have defined the definitions like fill factor and conversion efficiency. So, with that let us move on to the next topic. This is about solar cell.
Some doubt, sir.
Yeah, go ahead please. Yeah.
Sir, due to the incident of photons, a reverse current is produced, no, sir?
Come again.
Due to the incident of photons on
yes.
the.
Yes, yes.
So the net current will be less, no, sir? Then how it is efficient solar cell?
So, you are saying forward bias or reverse bias, you are saying?
Not this, sir. In the next slide, you have explained one point.
Which one?
Yes, sir. This one only.
Okay.
IL and ID.
Yeah, yeah.
This one, sir. The net current will be small, no, sir?
So, see, when you want to use, let me explain to you. When you want to use this solar cell, you need to operate in reverse bias. Under reverse bias, this current will be less. This current will not flow at all under reverse bias. This is nothing but current due to in the forward bias, right?
Yes, sir.
So, only this current will be flowing in the reverse bias condition. And now you can see that as number of photons keeps the falling on this the solar cell keeps increasing, corresponding IL keeps increasing. Understand? When you move from fourth quadrant to the first quadrant, as you are seeing in these characteristics, when you are moving from fourth quadrant to the first quadrant, you can see here, okay, that means you are moving from reverse to the forward. That means this curve almost the current will become equal to the forward current. That means because of this IL and ID, they are going to be opposite in nature, because IL is negative, ID is positive here. When you move from reverse bias to the forward bias, so this current will suppress and this current becomes dominant. So, therefore, this current due to the incident light approaches or follows this forward characteristics. Okay. In the forward bias, the solar cell operation and normal junction diode operation, it is same, they are not different. Whereas, in reverse bias, as we have seen already, if you do not apply light, this is the amount of current that flows, reverse saturation current, that is called dark current here. When you incident light on that, then proportionately the current keeps increasing. Okay. And now here, since we are using this in the fourth quadrant here, okay, the fourth quadrant you can see that as the current IL also starts flowing because of the incident light, and this current will not flow because you are operating in the fourth quadrant here. It is not under forward bias, it is under reverse bias. But this equivalent circuit what I have shown is applicable for both forward bias as well as reverse bias. Understand? This is the equivalent circuit of a solar cell. Assume that you want to operate solar cell in forward bias. How does it behave? In the forward bias, this current will not flow. You are not allowing even if you allow the incident light to fall on this, compared to this current will be less, because this current becomes dominant in the forward bias. Okay.
So that means it acts same like as photodiode.
Yes, yes. The photodiode, photo solar cell behavior is not at all different. It all depends on region of operation. Okay. If you use here the same photodiode what I have shown here in this third quadrant, the photodiode behaves like a photodetector. If you use same photodiode in the fourth quadrant, see all are PN junction only. Don't think in different way. PN junction in forward bias, the current flows in exponential manner. Okay, I am taking photodiode. Let us not worry about the PN junction. Let us call it a photodiode. Photodiode in forward bias, the curve is almost like this. Photodiode in reverse bias, it acts like a photodetector because as light keeps increasing, current also starts increasing. Photodiode same in fourth quadrant. How do you operate in fourth quadrant? I told you these extreme limits here, VOC and ISC. If you maintain voltage and current within these two limits, that means you are operating photodiode in the fourth quadrant. Now, the PN junction, instead of acquiring energy from the external source, it gives energy to the external source. I already told you this about because in this region the VI products, probably if you remember last class, if you get P is equal to V into I, the product of V into I, if it is negative, that means the circuit, the device gives energy, and if P is equal to V into I, if it is positive, if this is going to be positive, it is a passive device. If P is equal to V into I is negative, it is an active device. So, in this case you can see that the current is the voltage here is positive, current is negative, and if you take VA product, it is negative. That means the device here, instead of acting like a passive, it becomes an active. It gives energy to the external device, and this concept comes from the network theory. You just go through network theory and try to understand, okay, why this P is equal to V into I, a positive, okay, device will act like a passive source. Okay. When P is equal to V into I, if it is negative, the device will act like a, okay, it is negative, the device will act like an active source. Active in the sense it gives power to the other devices. So, therefore, if you operate the solar cell within this region, it generates energy instead of taking energy from the external power supply. Okay. Any other questions you have before we move to the other topic?
Yes.
Okay, all right. I think with that we have come to an end of solar cell. This material will be uploaded in the Google Classroom. Kindly go through that, and if you have any question, you can ask me later stage also. Okay, so let us move to the important parameters. Before that, let me cover up this. If somebody wants to see how exactly the photo detector looks like, this is the pin diode. You can see this is the actual the pin diode, and this is the photodiode what you see. It is a full spectrum silicon photodiode. Okay. Okay, let's move directly to the photo detector. This is the last topic which we want to cover. These things which we already covered in our handout, you can refer to that. This is what I told you, VOC and ISC. Okay. Energy band diagram we have seen. This is all the three quadrants we have shown simultaneously. You can see here the device behaves like a solar cell if you operate in fourth quadrant. Here device behaves like a photo detector. Here it is ordinary PN junction diode because it is operated in the first quadrant. First quadrant operation and its equivalent circuit. Second quadrant, not second, third quadrant and its equivalent circuit. Fourth quadrant and its equivalent circuit. Now this device will power this resistor. Here you need to power this device. So there is a supply here, you can see that, and you can also see the direction of current here. So here, since it is a photo detector, current flows like this, depending on the amount of photons injected. The current direction even in solar cell is also same as the photo detector. Okay, with that this structure we have already seen. We'll move directly to the photo detector. What do we mean by photo detector? Okay, the same photodiode that I have explained to you will work like a photo detector. That means it detects the photons. Okay, that means whenever photons are made to fall on this device, it generates an electrical energy. Okay, let us see the structure of a photo detector and its symbol, its characteristics. Okay, Though we have seen all together in a previous slide, specifically we are just focusing on the photodetector. So, one simple photodetector is the pin diode. Pin stands for P plus I stands for intrinsic, and N plus. That is where this photodetector is called as a pin diode. Okay. So, pin diode will work like a photodetector. What do we mean by photodetector? So, whenever light falls on this the surface of this, it converts this light into the equivalent electrical energy in this closed circuit. Okay. So, that is the working principle of photodetector. When number of photons here increases and corresponding current also keeps increasing here, okay, in this closed loop here. That is how the photodetector performs. And let us look into the structure here. This is a metal contact, as you can see here, the shaded portions regions indicate metal contact, and this P plus region you can see that which is a thin region which is very close to the surface. Okay. So, there is a lot of advantage here why we need to make it very close to this surface, because the energy which is photon energy which directly it can fall on the junction. Here junction is nothing but I area, intrinsic area. This is the junction, and this P plus region here and this N plus region behaves like a capacitor, because there is a intrinsic region here which behaves like an insulator. Okay. And we have connected an external resistance here. The current flowing through this dissipates power across this. Okay. So, there is an anti-reflection material coated here to focus the photon energy onto the P plus surface. Okay. So, now we have here the equivalent symbol here. So, this is almost same as solar cell. There is no much difference between solar cell and the pin diode. Structure remains same, and across this you are going to get a current here which is labeled as ID here. Okay. And this is a VI characteristics of this photodetector. Without this light falling on this, you can see it produces a dark current here, and as you keep increasing the photons on this, optical generation rate keeps increasing and current also keeps increase. Okay, you can see that this distance tells you the current here. As light intensity keeps increases and corresponding current also keeps increases. So, this arrow mark shows that intensity of light is increasing, corresponding current also keeps increasing here. So, that means the more and more current used to flow in this circuit as number of photons falling on the surface keeps increasing. Okay. So, this is about the photodetector. Let us look at energy band diagram of the photodetector. So, pin diode energy band diagram is as shown here. As you can see here, there is a P plus region here and N plus region, and in between these two there is an depletion region which you can see, this is I region. Okay. So, let us try to analyze this energy band diagram in 3 segments. First, let us analyze P plus region, what is going to happen in this region, okay, when the light is falling on this P plus region surface. So, when light falls on the P plus region, as you can see that it creates if H into mu photon energy, if this is greater than the band gap energy here Eg, then electron hole pairs, electron get excited and they move into the conduction band, and you can see hole in the valence band. So, this is called electron hole pair. Okay. And we know that in the P plus region or neutral P region, there is no electric field here because slope is 0, there is no electric field. Only process that is going to happen here is going to be the diffusion process. This diffusion process, what it will do is it moves this holes and electron to the edge of this depletion region. When holes and electrons comes to the edge of this depletion region, and here we know that the field, electric field acting from N plus region to the P plus region, this is the direction of the field which is from N plus to P plus, and this field is very strong. It pushes this electron to the N plus region, and hole is pushed back into the P plus region itself, because the hole direction and electric field direction are going to be same. So, hole will be pushed back into the P plus region and electron will be drifted to the N plus region. Within this depletion region, so the charge transport mechanism happens through a drift process, okay, because of the strong electric field here. Okay. So, here carrier transport is mainly because of the drift, whereas in the P plus region and this N plus region, the carrier transport will happen through the diffusion process, because there is no electric field in this N plus region and P plus region. Okay. And let us see here in the depletion region, if at all any electron hole pairs are created here due to the incident light. As you are seeing here, the hole is here and electron is here. This is an electron hole pair. The drift process now pushes electron to the n plus region and hole to the p plus region. Okay, this is what happens when the light is incident on the depletion region. If at all the electron hole pairs are there, immediately this electron is swept into the n plus, hole is swept into the p plus region. And now in the n plus region, the same process what we explained here in the p plus region is applicable here also. If the incident light here creates an electron hole pair, as you are observing here, the electron is in the conduction band and hole is in the valence band, and here the diffusion process can make this electron to move to the edge of this depletion region, and from here onwards charge transport will happen through the drift because of the electric field here, and this electron will be pushed back into the n plus region, and hole, because of electric field it is acting from n plus to p plus, this hole will be pushed into the p plus region. In a nutshell, what is happening here is, so this incident light is making these electrons to get collected in the n plus region and holes get collected in the p plus region here. In this, there is a charge movement or carrier transport is happening within this the depletion region, and this creates the current flow from n plus region to the p plus region here. So, as you keep increasing this the photons on this the entire photodetector surface, the current flowing from n plus region to the p plus region keeps increasing. Okay. So, this is what about the photo detector here. So, optical generation rate increases when the photon energy keeps increasing, and corresponding current also keeps increases. Okay. And also you can make an observation here, there is a split in the energy band, which you can see here, there is a Fermi level here, Fermi level has got splitted here, and this you can see Fermi level on the p side, and this is the Fermi level on the n side, and you can see this is operated, pin diode is operated in the reverse bias, and you can see the barrier height here is going to be Q times VR. VR is nothing but reverse voltage applied across the photo detector. Okay. So, this is Q times VR is nothing but the barrier potential in electron volt. Okay. So, with that I think we will move on to the next the important parameters. Let me jump to the important parameters, just skip this. Okay. Any questions so far about the working principle of the photo detector? No questions? Okay. Now, let us move to the important parameters of a photo detector. The first important parameter of photo detector is response speed. Okay. What do you mean by response speed? This is explained with this definition. Response speed means how fast photo detector would respond to the change in the incident light. Okay. If incident light the increases, corresponding current also should increase in the photo detector. If incident light decreases, corresponding electron current flow in the photo detector should decrease here. The question here is the response speed definition is how fast the photo detector can react or respond to the changes in the light. So, that is called the response speed, and there are several parameters which limits this response speed. Among them, the three are very popular and they are described as shown here. The number one is diffusion of carriers. Okay. So, diffusion of carriers, we know that diffusion happens in the photo detector p plus region and n plus region, and this diffusion process is going to be a slow process. Okay. And due to this slow process here, definitely it limits the response speed here. A drift process is very fast, but diffusion is going to be a slow process. Okay. So, now diffusion process has to be speeded up. We will see the mechanisms to speed up this diffusion process. The second factor which is affecting this response speed is going to be the transit time. What do you mean by transit time? If you look at this PN junction energy band diagram here, okay, this is the transit time. How much time an electron can take to move from edge of this depletion region, that's p side, p plus side edge depletion region, to the n plus edge of depletion region. How much time it takes? That is called the transit time. So, it all depends on now depletion width. So, if the depletion width is longer, definitely the electron will take more time, transit time will be very high. If depletion time is Okay, if the depletion width is very small, electron will take less time and the transit time will be less. Okay. So, the amount of time it should take should be very less. Okay. So, let us try to explain this. So, transit time means it is the amount of time an electron can take to move from either from p plus to n plus or from n plus to p plus here. In general, the charge carrier movement, amount of time taken by the charge carriers to move from either this the p plus to n plus or n plus to p plus is called as a transit time. So, this also limits the response speed here. Another factor which limits the response speed, okay, is nothing but the capacitance. The capacitance that is present in the depletion region. Okay. Now, go back to the again the structure of the pin diode. Okay, you can see here this is the here, as I told you, this region here p plus region here will act like one plate, this p plus region here, this n plus region will act like another plate. These two will behave like a parallel plates, and when we have a parallel semiconductors like this, it behaves like a capacitor, and there is a capacitance within this the pin diode, and there is a resistance here, and the product of this resistance and capacitance gives the tau, which is nothing but the delay time. Okay. Now, let us see here this capacitance is also plays a very important role, capacitance that is in the depletion region here. Now, what we expect to improve the response speed? All these three parameters should be as small as possible. For the very good response speed, we expect these three parameters should be as small as possible, that is diffusion of carriers, transit time and capacitance here. So, here capacitance means the capacitance, the reverse bias that dictates RC time constant. I showed you where exactly the capacitance is, and R is nothing but the external resistance what we have shown here. You can see this is an R, and C is here within the pin diode. So, these two dictates the RC time constant. So, now here is, since RC time constant is very high, because of this, okay, the response speed will become very less. Okay. The response speed of pin diode will be very slow because of RC time constant, which is high. Now, let us go more detail of these three parameters. Diffusion of carriers, you can see that how to reduce the diffusion length or diffusion distance. So, here you can make the p plus region very thin, and if it, since it is very close to the surface, light can directly fall on this, and this process of diffusion can be speeded up here. So, most of the light goes to the intrinsic region, because the p plus region whatever you are seeing here, this p plus region is going to be very thin and compared to the depletion region. So, therefore, so most of the light which is incoming photon light goes straight away into the intrinsic region, and where the electric field region is close to the surface, and it can since within the electric field there is a drift process which can speed up the charge carrier movement here. Next is the transit time. As already defined, transit time means it is the time that electron or hole take to traverse the distance in the presence of electric field. Okay, that is the transit time here. Now, capacitance is nothing but it mainly depends on the width, depletion width. So, the formula for this can be written as C, which is equal to epsilon into area of cross section of P plus and N plus region divided by W here. Now, let us see what should be the depletion width to be chosen. So, depletion width depends, if it is chosen small, what happens, what are its consequences, and depletion width if it is large, what are its consequences, pros and cons. Let us see in detail. And this we are taking with reference to three again parameters here. One is drift time and transit time. With reference to this, we will see what will happen if the width is small, and depletion capacitance, and finally the absorption. And let us assume that here the depletion width is very small. Okay, this case, if depletion width is small, the transit time will be very small, because you can see the distance between covered between these two will be very less. So, therefore, the transit time will be taken is very less. And let us see the capacitance here. So, capacitance now, since the depletion width is small here, so smaller the W, capacitance becomes higher. Okay. So, capacitance increases, depletion capacitance increases. Okay. And absorption here, photon absorption, that also keeps decrease, because when you make the width less here, this width less here, so the absorption becomes very less here. So, this arrow mark showing downwards indicates absorption is less for the depletion width smaller. On the other hand, if you see depletion width larger, transit time increases, depletion capacitance decreases, because this W is going to be large, this capacitance keeps decreases, and absorption, because area W is going to be large, there is a large absorption of photons within the depletion region here. Now, we need to choose, we have seen pros and cons of the small and large with depletion width. Now, let us choose this value as an optimal, so that you get more benefits, more response speed from the the photo detector. So, the depletion width must be chosen such that it should be the half of the modulation period. Let us not go more detail what do we mean by modulation period. It just this is a formula, we use it here, the value we use it here, and using that you can estimate what should be the optimal depletion width. Now, the modulation frequency, if I choose as 1 gigahertz, and the modulation time can be estimated by taking reciprocal of this, which is going to be 1 nanosecond, and since the transit time should be chosen half of this, so half of this becomes the 0.5. Yeah, transit time should be chosen half of this, which is 0.5 nanoseconds here, and saturation velocity of electron can be chosen as 10 to the power of 7 centimeter per second. And if you substitute this, if you take a product of these two, that gives you depletion width of 50 micrometer. And only two definitions we have left out here. One is quantum efficiency. Eta Q is quantum efficiency. It's a ratio of number of electron volt pairs generated and collected to the number of incident photons here. So this can be mathematically written as IL by Q. Incident photons can be written as P in by H into mu. This can be rearranged here in this this is what you are seeing here, okay, and H into mu here, this can goes to numerator, and this value you can substitute here, this H into mu and Q, this value which is found to be 1.24. So, the quantum efficiency value is IL by P into 1.24 electron volt by lambda in micrometer. Lastly, we have responsivity. Responsivity is labeled as R. Don't confuse with resistor here, even though responsivity is also labeled as R. It is a photocurrent which is in amperes by incident power, optical power in W. IL by P in, that is the mathematical relation, and you can use IL by P in here, and that's value, if you cross multiply this with quantum efficiency, it gives me this relation. Okay. This is what NQ, quantum efficiency times Q by H into mu. If we can rewrite this in other way, so this can be written as NQ into Q into lambda by H into C. C can be substituted as this C can be substituted as F into lambda, and substituting these values, it gives you 1.24. Okay, NQ into lambda by 1.24. This simplified formula for this responsivity. Lastly, the Avalanche Photodiode, these are the specially designed diodes to operate continuously in the reverse bias, because normal photodiodes will get destroyed if you continuously operate in reverse bias. These are all specially designed diode, so which you can continuously operate in the reverse bias. This can withstand the more avalanche the breakdowns. Okay. With that, I think we have completed almost all topics under module 2. Next class we will focus on the bipolar junction transistor. Okay. So that I will stop at this point, and if you have any questions, I can take it offline.